One day at high school, my maths teacher, Mrs. Vlachunashu Papadopoulos, discovered me behind the science lab trying to impress one of my many girlfriends. There I was, flower in hand, pulling the petals off one by one, saying, "She loves me, she loves me not, she loves me, she loves me not." Mrs. Vlachunashu Papadopoulos was fascinated. "Capanyara," she said, "you're a dork. That's no way to pick up girls. It's not logical. Why don't you count up all the petals on the flower, and if it's an odd number, she loves you, and if it's an even number, she doesn't." That simple logic amazed us both, and you know, thinking back, it was probably that very moment that stirred up my interests in mathematics, culminating in my love for calculus.
Calculus is a mathematical tool for dealing with change, nature's most fundamental process. Nothing in the world is permanent. Everything changes, sometimes fast, sometimes slowly. We're born, we grow to maturity, then later we die. All plants and animals repeat that cycle. On a slower timescale, the landscape of the Earth changes, and the continents move from one place to another. The Earth itself moves around the Sun. Change is inevitable, but difficult to analyse. Nowadays, we're familiar with the idea of using time as part of the description of nature, but for many centuries, it was beyond the scope of mathematicians. It was only in the late 17th century that calculus was invented, opening up this new and powerful area of mathematics. Calculus is divided into two areas. Differential calculus uses the technique of differentiation to find derivatives, while integral calculus uses integration to find integrals. Differentiation and integration are both needed to analyse change. They join the basic mathematical operations of addition, subtraction, multiplication, division, and taking roots. Differentiation is used to compute the rate at which one variable changes in relation to another variable at any particular instant. Integration is the reverse process, where information about change is used to describe the variables that are changing. Differentiation and integration have many practical uses.
You know, you just can't put up a bridge like this without knowing something about the amount of stress that each metal component can cope with. Now, give me the spanner. No, not that one, the big one. In engineering, calculus is used to analyse the forces acting on these metal parts so that buildings and bridges can be designed to function safely and efficiently. In medicine, calculus is used in the plotograph of this spirometry test to measure lung function and capacity. How was that?
And calculus enables predictions to be made about the greenhouse effect, analysing measurements of atmospheric carbon dioxide to predict its future growth rate. So calculus is an important part of mathematical theory and an essential tool of scientific endeavour. But more than that, it's one of the truly great ideas in the history of human thought. It's comparable to the invention of printing, computers or air travel, even the art of Rembrandt or the music of Mozart. Like these, calculus has changed the way we think about the world. Like so many areas of mathematics, calculus began in the minds of the ancient Greeks. They examined the basic problems of calculus in a geometric setting. They were the first to use the concept of an infinitesimal, a simple idea, yet remarkably powerful. To them, an infinitesimal was a quantity so small that it couldn't be divided further, But since it was still greater than zero, it could be used as the building block of a finite quantity, like a length or an area. Any curve can be divided into infinitesimals, pieces so small they can be treated as if they were straight. One of the most famous Greek mathematicians was Archimedes, who lived in the 3rd century BC. He developed a method of finding the area of curved figures by slicing them up into smaller and smaller pieces. It's similar to our current method of integral calculus, but Archimedes didn't give any general rules or notations for his methods. The simplest curved figure is a circle. We see them everywhere. But how can we find their area if we don't know the formula? Here's the method used by Archimedes over 2,000 years ago. First, he drew 2 squares, one touching the circle on the inside, the other touching the circle on the outside. The area of the circle is obviously somewhere between the areas of the 2 squares. Next, he changed the squares into octagons, figures with twice as many sides. The space between them has now decreased in size. Then the polygons became 16-sided, and so on, continually trapping the area of the circle between the area of the inner and outer figures. Since these figures have straight sides, we can easily find their area. By this method, Archimedes found that the area of the circle is pi times the radius squared, or pi r squared. The key point in this process is to divide the circumference of the circle into infinitesimally small pieces that can be treated as if they are no longer curved. This is the essential technique of integral calculus and is always used to find any curved area. The Greeks also looked at the problem of constructing a tangent to a circle, a straight line that touches the circle at one point. A golf club forms a tangent when it hits a golf ball. Under magnification, the straight line of the tangent is indistinguishable from the curve. In fact, when we magnify any point on a circle, it will eventually look like a straight line. Again, we're dividing the circle into infinitesimally small pieces that can be treated as if they are no longer curved. Any smooth curve will look straight when we zoom in on a small part of it. This is the essential technique of differential calculus and is used any time we want to find a tangent to a curve. This idea waited for many more centuries before it was developed further and used to build a complete theory of calculus. In the meantime, Europe was going through the Dark Ages. With most people involved only in the basic struggle for survival, learning was kept alive by a few scholars in monasteries and convents. Mathematics was not so much a practical subject as a matter for philosophical discussion. However, one practical development in the prehistory of calculus was made in this period. This development concerns ideas of motion. Integration can be represented geometrically as the process of finding an area. But as the area under a curve can also represent a physical quantity, such as distance, an integral can therefore represent a physical quantity as well as an area. The 14th century French mathematician Nicole Oresme worked out a method for displaying these ideas graphically. Oresme's graphs used 2 lines at right angles to each other, called axes. If we let the horizontal axis represent time and the vertical axis represent velocity, then the area under a graph of velocity against time represents the distance covered. Consider a car driven steadily at 100 kilometres an hour for 2 hours. If we graph the velocity against time, it will be represented by a straight line. The total distance covered during the drive will be 200 kilometres, which is represented by the area under the straight line. That is, the rectangle with a length of 2 and a height of 100. But what if he doesn't drive at the same velocity all the time? What if he varies his speed?
No wonder my happy heart sings.
Well, the graph of velocity against time will now be represented by a curve, but the area under the curve will still represent the total distance travelled in 2 hours. We can now measure the curved area and find out the distance travelled. This shows that an area can represent a physical as well as a geometric quantity, and explains how integral calculus can be applied in practical situations. We can also apply differentiation to a physical situation. Differentiation can be represented geometrically by constructing a tangent and finding its slope or gradient. But the slope of a tangent to a curve can also represent a physical quantity such as velocity. If the horizontal axis shows time and the vertical axis shows distance, then the slope of a tangent to a curve will represent the rate at which distance is being covered, that is, the velocity. For example, when a parachutist jumps out of a plane and opens her parachute, she will fall to Earth at a constant velocity.
If I open my parachute at 600 metres and it takes me 100 seconds to get to the ground, then my velocity is 6 metres per second. As you can see, on a graph of height against time, this is represented by a straight line with a slope of -6, my downward velocity.
However, if her parachute failed to open, she would fall to Earth at an increasing velocity. The graph would then have a curve like this. At any point in time, we can draw a tangent to the curve. Its slope represents the instantaneous velocity at that particular moment in time. This demonstrates that the slope of a tangent can represent a physical as well as a geometric quantity, and explains how differential calculus can be applied in practical situations. Europe emerged from the Dark Ages to the Renaissance, the great flowering of intellectual discovery. The late 16th and early 17th centuries were periods of intense activity for mathematicians. The age-old problems of curved areas and tangents were tackled with renewed intensity using improved tools like better algebraic notation and newly developed graphical methods. Algebra and geometry were united into the new area of coordinate geometry. But not everyone was happy. In Renaissance Italy, mathematics was a very competitive career choice. In fact, gang warfare between rival groups of mathematicians was commonplace, with attacks often leading to assassinations. One surviving Italian was Bonaventura Cavalieri, who used the method of infinitesimals to find curved volumes.
Thank you, Frank. As an example, let's look at a vital problem. Finding the volume of the froth on a cappuccino. Now, Cavalieri would consider it to be made up of a lot of extremely thin slices. Each slice thin enough to have straight sides like a cylinder. We know how to calculate the volume of a cylinder, so we just find the volume of each slice and add them together to find the total volume of the froth. Of course, we could have also worked it out by simply spooning the froth into a measuring cup. But that wouldn't have taught us a thing, would it? Eh? Get out of here.
Johann Kepler was a mathematician who lived in Prague. He's best remembered for his work describing the elliptical orbits of the planets around the Sun.
But he was also very poor, and so he turned his mathematical abilities to more worldly pursuits and picked up quite a bit of extra income from astrological predictions and solutions to practical problems. One problem was how to make a wine barrel that will hold the maximum amount of wine while using the minimum amount of wood in construction. Today, such problems are known as maximum or minimum problems and are still solved by using calculus methods. Kepler considered different shaped wine barrels, each made from the same amount of wood. So, will a tall, skinny barrel hold more wine than a short, fat one? Or will all shapes have the same volume? I don't know. Let's find out.
If we draw a graph showing the radius of the barrel on the horizontal axis and the volume of the wine it contains on the vertical axis, we get a curve like this. As the radius increases, the volume also increases up to a maximum, then decreases as the radius gets larger. The maximum point on the graph is called a stationary point because the volume of wine is neither increasing nor decreasing. Using this graph, Kepler found the barrel shape that can hold the largest amount of wine while using the same amount of wood.
But something was still missing. One coherent theory that brought together all the isolated techniques and methods of solution.
Isaac Newton and Gottfried Wilhelm Leibniz. Independently, in separate countries, and within just 10 years of each other, they invented calculus as we now know it. Their methods were remarkably similar. Each developed a clear system of solving problems using differentiation and integration. Newton actually made his discoveries first, but he was a shy man who disliked controversy, so he delayed publishing his results. Leibniz better understood the value of publicity. He published his ideas first, and in the long run, his notation has proved more successful. It was Leibniz who first used the letter D to stand for differentiation and the long S symbol to stand for integration. So what exactly was this breakthrough? If we look at a point on a curve, we can see how Leibniz explained his method of differentiation. As we zoom into the point, the curve becomes more like a straight line, the tangent to the curve at that point. We can find the slope or gradient of this line as rise over run, or the change in y over the change in x. Leibniz used dy to represent the change in y and dx to represent the change in x. So dy over dx represents the slope of the tangent and also the slope of the curve at that particular point. For Leibniz, integration represented the concept of summing to find the area under a curve. Consider that area as being made up of infinitesimally thin rectangles. Each rectangle has height y and width dx, so its area is represented by y dx. The total curved area is the sum of the areas of all the rectangles. It's represented by the integral of y dx. In fact, integration is actually the inverse process, the opposite of differentiation. They are related in the same way as other mathematical operations, like squaring and taking a square root. This inverse connection is central to calculus and is formally proved in the fundamental theorem of calculus. So while others had developed similar methods, it was the linking of these processes into one all-encompassing theory that secured a place in history for Newton and Leibniz. Applying these newly developed methods to a large variety of problems, Newton investigated the idea of curvature, or as he put it, the quantity of crookedness of a curve. A straight line has zero curvature. A gentle curve has small curvature, and a tight curve has large curvature. A curve with positive curvature is called concave up, while one with negative curvature is called concave down. Any point where there is a change in concavity is called a point of inflection. Differentiation methods are used to find the curvature and determine where the points of inflection are. Calculus was also applied to the major scientific, engineering and military problems of the 17th century. Telescopes and microscopes were being built for use in astronomy and biology. To design the lenses and work out how light rays travel through them required the ability to find tangents to the lenses. Differentiation was used extensively in this work. In astronomy, integration methods were used to find the length of the curved path of a planet's orbit. And maximum-minimum problems were still very important. With cannons constantly used in battle, generals needed to work out how far and how high a cannonball could be fired.
Fire!
you doing? You know, another problem studied by Newton, Leibniz and their contemporaries was the relationship between acceleration, distance and velocity in a continuously changing situation. Let's get on the road. You see, average velocity is calculated as distance travelled divided by time taken. But people were often interested in instantaneous velocity, that is, the velocity at a particular instant of time. These days we're used to seeing instantaneous velocity displayed on the speedo. But in those days they didn't have any. So, without a speedometer, how do we calculate instantaneous velocity? We'd like to use the formula distance over time. But at a particular instant in time, the car appears to be still, as there is zero distance travelled in zero time. However, the expression 0 over 0 is meaningless. Good shot. Using the new invention of calculus, the precise meaning of instantaneous velocity was found. If distance is y and time is x, then the instantaneous velocity is the ratio dy over dx.
But when Newton and Leibniz calculated with these infinitesimal quantities, were they using small, finite amounts of time and distance? Or were they really using the meaningless ratio of 0 over 0? So do the processes of integration and differentiation give us approximate or exact answers? Calculus still had some logical and philosophical concerns, even though its methods were easy to apply to practical problems.
It took another 100 years of work to completely understand and answer these concerns. A new concept had to be invented, the concept of a limit, before calculus could move forward on a strong foundation. Hello? Eddie? Oh, there you are. Now, you've looked at the development of calculus from its beginnings in ancient Greece, medieval Europe, and the Renaissance, through its invention by Newton and Leibniz at the end of the 17th century, and the solutions to the remaining theoretical problems 100 years later. So, let's have a look at a couple of modern applications of calculus.
The first concerns the use of computers to design buildings. With computer software using techniques of calculus, architects can design and display a building from various points of view so fast that it looks like we're walking around the building. Using this virtual reality, a building can be investigated in detail long before it's actually built. In fact, objects can be investigated which may never be built. This program's opening graphics represent a famous problem in computer science. Calculus is used to find tangents to follow rays of light as they travel around various reflecting spheres above a checkerboard.
Calculus is an important part of mathematical theory and an essential tool in all areas of scientific endeavour. But more than that, calculus is one of the great ideas in the history of human thought. Thank you, Mrs. Vlahounashiu Papadopoulos. She loves me. She loves me not. 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 She loves me. She loves me.